And test 2 is covering chapter 13 and chapter 14. Right, so chapter 13 has to do with rate constants and rate laws. And chapter 14 has to do with equilibrium. Okay, little k and big K. Right, so one of the problems on the exam is a rate law. So we're given this equation and we want to figure out how fast this reaction is going to proceed. Right, so the rate law has this form. It has this form, and the form is this. Why is that computer not showing up? Okay, rate is equal to K. So you start off with some concentration of reactant. This reactant is called NH4 plus ammonium ion. And this is going to decay with some exponent A. And then this reactant, the second reactant, how much you start off with, the initial concentration. And it's going to decay with exponent B. So our job here in finding the rate law is to determine K and the exponent A and the exponent B with the right units, with the correct units. So first thing I'm going to do is I'm looking at this data table and I see I'm going to compare experiment 1 and experiment 2 because I can kind of cancel these out. So we will compare experiment 1 with experiment 2, which means rate 1. Okay, look at my equation now. Rate 1 over rate 2 is equal to K times NH4 positive raised to the power of A times NO2 minus raised to the power of B. Okay, look at my equation now. NH4 positive, this is called the ammonium ion, and NO2 minus is called the nitrite ion, nitrite. Right, so now what we're going to do is we're going to substitute. Okay, we're going to substitute our values here. So let's begin substituting. Rate 1 is 7.20 times 10 to the minus 6. Can you guys read that? Lee, can you read this in the back? Yes? Okay. Okay, what's rate 2? 3.60 times 10 to the minus 6. Okay, what is NH4 plus for rate 1, experiment 1? 0.24 big M raised to the power of A. We want to find out these exponents now. This is rate law, rate law. Okay, NO2 minus raised to the power of B. What is NO2 minus? 0.10 molar, okay, raised to the power of B. Okay, let's do rate 2 now. Okay, 0.12 M raised to the power of A and 0.10 M raised to the power of B. So I want you guys to recognize the K's cancel. 0.10 to the power of B and 0.10 to the power of B cancel. And then 7.20 times 10 to the minus 6 divided by 3.60 times 10 to the minus 6 on your calculator. This is equal to 2. Okay, mole over seconds gets canceled. 0.1 to the power of B, 0.1 to the power of B cancel. K's cancel. So 0.24, by the way, the M's cancel. So 0.24 divided by 0.12, that whole thing gets raised to the power of A. Right? Okay, I'm just taking the exponent A and then pushing it out. So 0.24 divided by 0.12 is 2 to the power of A is equal to 2. So what to the power of A, 2 to the power of what is equal to 2? 1. It's very good. So NH4 plus decays with first order kinetics. So that rate law sheet with all the equations, you're going to use the first order. Okay, first order decay. Now I'm looking at this. I'm going to compare 2 and 3 now. Okay, I'm going to compare 2 and 3. So we can do experiment 2 over experiment 3. Okay, so rate 1 for experiment is going to be rate 2 over rate 3. Okay, K times NH4 positive to the power of A, NO2 minus to the power of B. K times NH4 positive to the power of A, NO2 minus to the power of B. Alright, so let's substitute our values in. Rate 2 is 3.60 times 10 to the minus 6 molar over second. Rate 3 is 5.40 times 10 to the minus 6 molar over second. Excuse me. Okay, I'm going to substitute the values here. NH4 positive for rate 2, experiment 2 is 0.12. Okay, raised to the power of A. We know A is 1. NO2 minus for rate 2, experiment 2. I'm looking at my table and I'm getting 0.10 molar raised to the power of B. And then we'll do the same thing for rate 3, experiment 3, plugging those values in. 0.12 molar A, 0.15 molar to the power of B. Alright, so the molar over seconds cancel, K's cancel, the 0.12 cancels. So what's 3.60 times 10 to the minus 6 divided by 5.40 times 10 to the minus 6? What is that on our calculator? If you do that on your calculator, what will you get? What will you get in your calculator? You'll get a decimal. What is that decimal? 0.66666666, on and on forever. So 0.66666666, what is that? Sorry? 2/3. 2/3. Okay, 2/3. 1/3, Carolina's 0.3333333333. Okay, 2/3 is 0.66666666. Alright, so this is going to be 2/3, and what is this is going to be 0.10, the m's cancel, divided by 0.15. We'll raise that whole thing to b. So what's 0.10 divided by 0.15? You guys getting 0.666666? Okay, so what's 0.66666666? This is 2/3 to the power of b. Alright, so what is b now? Okay, so b is equal to 1. So just like NH4, NO2 is going to decay with first order kinetics. So now, okay, so now let's complete this. We're not totally done just yet. We want to complete our problem here. Rate is equal to K times NH4 positive raised to the first power times NO2 minus raised to the first power. Okay, so this is not the answer just yet. By the way, the overall order of this reaction is 1. The overall order of this reaction is 1 plus 1 is 2. Okay. So NH4 positive decays with first order kinetics raised to the power of 1. NO2 minus decays with first order kinetics raised to the power of 1, so 1 plus 1 is equal to 2. So we say the overall order of the reaction is 2. Right, so we're not done yet. We're going to find K. Okay, so which experiment do you want to use to find K? 1, 2, or 3? I'll just pick 1, okay, but you can pick 2 or 3. So we will use experiment 1 to find K. Okay. But you can use 2 or 3. It doesn't matter. So what is the rate for experiment 1? The rate for experiment 1 is 7.20 times 10 to the minus 6 molar over a second. Okay, the concentration of NH4 is going to be raised to the 1 power, raised to the first power. 0.24 molar raised to what power? 1. And what is NO2 for experiment 1? It's 0.10 molar raised to what power? 1. Okay. So K is going to equal to 7.20 times 10 to the minus 6 molar over second divided by 0.24 m times 0.10 m. Okay, just isolating K, solving for K. All right, everyone check this out. Okay, this m cancels out with this m. My m in the denominator stays. My seconds in the denominator stays. I'm just saying this because units matter. Units are going to matter. So what is 7.20 times 10 to the minus 6 divided by 0.24 times 0.10? Okay, parentheses here. 0.24 times 0.10. 0.0003. Okay, we want to make a big deal of the units here. Okay, m in the denominator, seconds in the denominator. This is equal to K. Right, now you can also do this. K is equal to 0.0003 m to the minus 1 seconds to the minus 1. Okay, that's also perfectly fine. So our final answer, this is what I want you to put on the exam. Our final answer is going to be this. Rate is equal to 0.0003 m to the minus 1, which is m in the denominator, seconds to the minus 1, which is seconds in the denominator, times NH4 positive raised to what power? 1 times NO2 minus raised to what power? 1. And this is our final answer. This is what I want you to write on the test. But we have a way to check our answer. Okay, how can we check our answer? Okay, we'll use experiment 3 or 2. Okay, we'll use experiment 2, or we can also use experiment 3, but we'll use experiment 2 to validate our answer, to check our answer. So what is the concentration of NH4 in experiment 2? 0.12 molar raised to what power? 1. Raised to the 1 power. What about NO2 minus for experiment 2? 0.1 molar raised to what power? 1 as well. Overall order of the whole thing is 2. So what is this equal to? Okay, let's check it out. Three times 0.12 times 0.10. 3.6 times 10 to the minus 6. Okay, this m cancels out with that m. Everyone see this? This m cancels out with that m. And I'm getting 3.6 times 10 to the minus 6 molar over second. And look at that. Okay. Right on target. So I bet if you plug in experiment 3, you'll get the same thing, 5.4 times 10 to the minus 6. So I'm pretty confident this is the right answer. Okay. All right, let's look at part C here. All right, so this is what you want to do. This is the pipeline for the test on Tuesday after spring break. So what is the rate when the concentration is 0.39 molar for ammonium ion and 0.052 molar for nitrite ion? So we got our rate law already. Alright, so we're going to plug in NH4 positive to here, 0.39. Okay, molar raised to the 1 power. And then we'll plug in NO2 minus 0.052 raised to the 1 power. Okay, so this should equal to the rate. Remember, rate means how fast. Okay, you can think of rate as meaning speed of the reaction. Not in miles per hour, but in molarity per second. And what do we do when we get that? .08 times 10 to the minus 6. Okay, molar over seconds. So this is the answer. You're just plugging things into the newly established rate law, which you found using this data. All right, can we do this on the exam? All right, so make sure you get practice on doing the rate law problem, something similar to this on Tuesday's test. All right, let's move here to another problem. Our next problem involves the Arrhenius equation. So I'll give you this on the exam. And here you're going to have to calculate the activation energy. So what is the activation energy? Okay, it's like the hump. Okay, the energetic hump. Think of putting a sweater on a child. It takes a lot of work and effort. But once you put in that energy, everything goes downhill from there. It becomes easier after a lot of expenditure. So this hump is called the activation energy. Okay. okay, whether it's exothermic or endothermic. So the energy that the reaction must get in order to form products, we call that EA. The units of this are going to be in joules per mole, or, you can just say kilojoules per mole. Okay, so make sure you are good with the units. All right, so a first order reaction has a rate constant of 1.0 times 10 to the minus 3 at 25 degrees. So we'll call this K1 at T1. So K1 here is 0.001. If the rate constant K increases to 3.5 times 10 to the minus 3 at 45 degrees, we'll call this K2 at T2. So this is 0.0035. What is the activation energy for this reaction? So we want to solve for EA here. Okay, R is something I'll give you on the test, which is 8.314 joules over a mole Kelvin. Okay, 1 over T2 is, we got to convert it to Kelvin. I saw in the last exam, students were putting this still at 45 degrees C. So we want to convert it to Kelvin for this particular problem. 318 Kelvin. Okay, minus 1 over T1. What's T1? 25 plus 273. Okay, 298 Kelvin. All right, so are you guys comfortable in solving for EA? Okay, this is also called the activation energy. So it's going to be 1 over 318 minus 1 over 298. Let's do this fraction together. So you can do this with me on the calculator. 1 divided by 318 minus 1 divided by 298 is this number divided by 8.314 is this number here. So the kelvins cancel. The mole in the denominator of the denominator goes to the numerator, and the joules stay in the denominator. So this right-hand side of the equation is minus 0.0000253. I'll put in some extra digits here. Okay, moles over joules. And then what's natural log of 0.0010 divided by 0.0035? Okay, we're going to do this fraction first. So 0.0010, do the fraction first, divided by 0.0035. And I'm going to take the natural log of this. And I'm getting minus 1.2527. I'm just putting some extra digits here, just, By the way, there's an EA here I forgot to mention. Yeah, there we go. There's the EA. So we will solve for EA by cross multiplying. Okay, solve for EA by cross multiplying. So let's go ahead and do that. Okay, the joules goes here. The minus 0.00002539 goes at the bottom. So EA is going to equal to 1.252763 joules divided by 0.0000253 moles. And what is this on our calculator? Are you guys getting 49,341, something like that? Or something close to it? Yes or no? Yep. All I need is one person on the calculator to confirm, so I'm good. You can also write this as 49.3 kilojoules per mole, okay? So I'll accept this, which is fine, and that is also good. Alright, so something like this on the test. Make sure you're comfortable in doing this. If not, you can just follow along in the video, or, that will be posted later in class or after class. Alright, so we're solving for the activation energy. Alright, so Arrhenius equation, rate law. Another problem on the computational side is the ice table. So let's go ahead and do an ice table problem here. So there's a lot of plug and play, plug and play, plug and chug. So So we're going to do a lot of ice tables after spring break. So this is our first foray into ice tables. So first of all, with ice tables, you are looking at an equilibrium. How do you know this reaction is an equilibrium reaction? Okay, the arrows tell us this is an equilibrium reaction. And basically you have the equilibrium concentrations of H2S, I2, and HI after 0.035 molar of HI is added. So this is what this means. So let's say you have a bottle of this chemical, 0.035 molar HI. Okay, that bottle does not contain 0.035 molar of HI. What else does it contain? What else does it contain? Okay, it's going to contain some H2 and I2. Okay, so initially, if you have 0.035, finally, or at equilibrium, you're going to have a different value. So this is where we construct our ice table. Okay, according to the problem, initially we have 0.035 molar of hydrogen iodide. Okay, so the I in the ice table stands for initial. Okay, that's not all that's going to be in that bottle. Some of it, okay, some of it will go this way. So that change we're going to call C. And it's not going to be minus X. It's going to be minus 2X. Okay, why? Okay, because of the stoichiometry, or the coefficient 2. And we stated it's going to shift left. Okay, someone asked in the Monday class, why does it shift left? Because this is what you start off with. Okay, so some of it in equilibrium is going to, some of it will go back. Okay, so change, so minus 2x. Someone also asked why 2? Okay, because of the 2 here. Okay, minus 2x.
So it's minus 2x because the 2 is moving over to the
because there's 2 moles of this HI.
Okay. And so, it's minus 2 instead of plus because it's moving over?
Yeah, so initially all they tell you in the problem, Bailey, is you have 0.035 molar of this. But when this is all said and done, you won't have 0.035 molar of this. Why? Because some of it will go this way. We want to figure out how much H2 and I2 and HI is there when this equilibrium gets firmly established. So concentration of H2 is X, the concentration of I2 is X, concentration of HI is 0.035 molar minus 2X. Okay. Okay, so let's plug into our equilibrium expression, our equilibrium constant. Okay. Concentration of HI. What should I do with that HI? Very good, thank you. Good job. Square it. Nice work. And then concentration of H2 divided by also concentration of I2 in the denominator. So KEQ given to us here is 50.5. Okay, 0.035 minus 2x whole squared. Okay, we're going to plug in the equilibrium concentrations that go to equal the equilibrium constant. Okay, HI at equilibrium is H2 at equilibrium is x, excuse me. I2 at equilibrium is x, so that's x squared. Okay. So we're going to take the square root of both sides of the equation to solve for x. Okay, so take the square root. Okay, what's the square root of 50.5? Uh, 7.1063. Okay, a minus b whole squared, if you take the square root of that, it's just a minus b. Okay, and the square root of x squared is what? It's x. Okay, so we're taking the square root to solve for x here, at both sides. So multiply by x. Let's move the minus 2x to the other side of the equation. Minus 2x. That will make it plus 2x. So 7.1063 plus 2 is 9.1063x. Equals 0.035. X is equal to 0.035 divided by 9.1063. Alright, so this is just algebra. Okay, this is really not chemistry. So one thing is when we solve for x, our units are going to be molar. Big M moles over a liter. I'm getting 0.00384. We'll do 0.0038. Okay. And that is x. But what does that x really mean? Okay, so that x really is this x, which is the concentration of H2 at equilibrium. That's point number 1. Point number 2 is that this x that we solved for is really this x, which is the equilibrium concentration of I2 at equilibrium. Okay, and then finally, point number 3 is that 0.035 minus 2x, plug that in, will give us the final equilibrium concentration of HI. So our final answer, okay, at equilibrium, okay, the concentration of H2 is going to equal x, which we calculated it as 0.0038 molar. Okay, don't forget the units. The concentration of I2 is going to be X, which is 0.0038 molar. And then the concentration of HI is going to be 0.035 minus 2X, which we calculated as 0.0038. Okay, let's quickly find that out in our calculator. Okay, so minus and then plus 0.035, 0.0274 molar. So this is our final answer. Okay. There's a way to check our answer. Okay, how will we check our answer? What can we do? Okay, we'll take this, plug it back into here, and what should it equal? Okay, what should it equal? Okay, it should equal 50.5. Okay, so we have a way to check our answer to make sure that it is indeed 100% correct. So we'll check our answer. Okay, so HI squared is 0.0274 squared divided by H2, which is 0.0038. And I2 is 0.0038. We're going to check our answers with we're going to check our answer. And what does that equal to? Let's do that quickly on our calculator. 274 squared divided by 0.0038 times 0.0038. 51.9. That's good enough. It's close enough for me. Okay. 52. This is 50.5, 51. I think it's good. All right. So I would say close enough. Okay, so any questions on this? So in this type of problem, you're going to go back and you're going to take the square root to find x, plug that x back in to the ICE table. All right, so let's do one more computation problem here. And then let's see if I can find a clean sheet. Guys took all my practice tests. Right, so this type of problem involves looking at Q. Okay, looking at Q and then comparing it to K. All right. Notice here that we have gases. So with gases, you're going to have a KP, so pressure. The P here stands for pressure. All right, so initially, we'll highlight that term initially. It contains I2 as 0.1, Cl2 is 0.1, ICl is 0.1. Find the equilibrium partial pressures of H2Cl2 and ICl at this temperature. Okay, so let me do that here. So I'll rewrite the equation. So the Kp here is going to equal to the pressure of ICl squared. Okay, why do we square it? Because the problem was balanced and we have a 2 here. Okay, divided by I2, pressure, times pressure of Cl2. Okay. Okay, so 81.9 equals the pressure of ICl. What is the pressure of ICl? Iodide monochloride. 0.10 atm atmospheres. And notice, okay, these are pressure units. 0.10, which 0.10 atmospheres, we should square it. Okay, we should square it. Why do we square it? Okay, because that's what the law of mass action tells us to do. So in the problem, this was 0.100 squared. There's no units, so don't worry about units. Divided by the pressure of I2. What's the pressure of I2? Okay, it's the same as the pressure of Cl2, which is 0.10. Okay, atmosphere. So 0.1 and 0.1. So we have a problem here. Okay, what is this problem? The problem is that we plug in these pressures, and we put it into the law of mass action, and it doesn't equal to the equilibrium constant for pressure. Okay, in fact, 0.10 squared divided by 0.10 squared is 1. Okay, so it does not equal to this. So we have a problem. We are not at equilibrium. So which way should the reaction go to get to equilibrium? So here you want to use the gator rule, alligator rule. So for that rule, we're going to put Q first and compare it to K. So this K, in terms of pressure, is 81.9. This Q, which we just calculated from these pressures given to us in the problem, is 1. So which is bigger, Q or K? Okay, K is obviously bigger. So which way do the gator jaws point to? Okay, so this will shift to the right. So when we make our ice table, okay, our next step is to make our ice table with it going to the right. Alright, so I2 plus Cl2 goes to 2ICl. Okay. So initially we have 0.10, 0.10, and 0.10. Okay, it's going to shift to the right. Okay, so this is going to be minus x, and plus 2x. Okay, so this equilibrium is going to shift to the right. Because we're not at equilibrium. What will it need to do to get to equilibrium? Shift to the right. Okay, put Q first. The alligator jaws are pointing to the right, which is the product side. Alright, so finally at equilibrium, this is going to be 0.100 minus x, 0.100 minus x, 0.100 plus 2x. Okay, let's plug that into our Kp here. Kp is pressure of ICl squared divided by pressure of I2 times pressure of Cl2. So Kp is 81.9 given to us in the problem. Equals 0.100 plus 2x squared divided by 0.100 minus 2x. Okay, I'm going to square that too. Okay, this is 0.1 minus x, this is 0.1 minus x. Okay, why do we shift right? Okay, the gator rule tells us to shift right because these pressures given to us in the problem are not equilibrium pressures. All right, like before, we're going to take the square root of both sides. All right, the square root of 81.9 is probably 9 something, if I were to guess. 9.05, something like that. 9.05 equals 0.100 minus 2x. Okay, because the square root of the square is we cancel, and the square root of the square also cancel. this is 0.100 minus x. I'm sorry. All right, 0.100 minus x. All right, so now we'll solve for x here. 90.5 times 0.100 minus x equals 0.100 minus 2x. Okay, this is algebra now. Let's carry this through. 90.5 times 0.1 is 9.05 minus 90.5x equals 0.10 minus 2x. Okay, so I'm going to move, what can I do here? I'm going to move this minus 90.5 to this side, and the 0.1 to the other side. So this gives me 9.05 minus 0.10 equals 90.5x minus 2x. Okay, this algebra can get pretty head spinning.
Did we move a decimal from 9.05 to 90.5?
Because 90.5 times 0.1 is 9.05. Am I correct? I'm just distributing this.
From the step above, we're at 9.05.
Oh, okay. Thank you. So what's 9.05 times 0.1? 0.905. Okay. Yeah. All right. Thank you, guys. Thank you. Okay, so 0.905 minus 9.05x equals 0.100 minus 2x. Okay. Does that look okay? I'm going to need you guys to help me. All right, 9.05. Okay, I think that's okay. And then 0.905 minus 0.100 equals 9.05x minus 2x. Okay, so just making sure 7.05x equals, what's this, 0.805? 0.805. So my only word of caution is just be careful of the math. I'll always try to give partial credit if I could see your thought process. And hopefully I'm okay. So what does x equal to? 0.114 atmospheres? That doesn't make any sense.
So on our ice table, why is it 0.1 minus 2x? We went from plus 2x, our ice table to minus 2x.
Oh, okay. So there's a transcription error.
Also, what's more, shouldn't like the 905, like 9.05 minus 0.100, shouldn't it be 8.95? Why is that?
No, this stuff is right. Okay, so this should be 0.100 plus 2x. Yes, okay. All right, so let's go through this again. I want to thank you guys for helping me. All right, so 90.5 times 0.100 minus x equals 0.10 plus 2x. Okay, are we good with that? 9.05. Okay, we good? Okay. So that makes it 0.905 minus 9.05x equals 0.100 plus 2x, right? Okay. 9.05, moving it to the other side, plus 2 makes it what? Okay. Yeah, so basically I put a minus here, but it should have been a plus. Okay, so minus 9.05 moving it to this side should be 11.05. 0.905 minus 0.1 is 0.805.
Wait, why is it 0.805?
Because 0.905 minus
Oh,
0.1.
okay.
Yeah, good. All right, I'm going to cross my fingers here and hope this is correct. 0.07, this makes a lot more sense. 0.073 atmospheres. Okay. Oof. Okay, so there's a transcription error. 0.100 plus 2x. I put a minus 2x there, so you found my error. So I thank you guys for that. And then our final answer here, final equilibrium pressure. Okay, I2 is going to equal to 0.10 minus 0.073. What is that on our calculator? .027. Okay. CL2 should be the same thing. 0.10 minus 0.073, which is 0.027 atmospheres. And then finally, ICL should equal to 0.10 plus 2 times 0.073. And what is that on our calculator? 2 times 0.073 okay, plus 0.246. Okay. Is that what you got, Carolina? Something close to this? Okay, good. That too. All right. All right, so I can tell you where I made my mistakes. Okay, everything was right up to here, but I put 0.10 minus 2x when it should be 0.10 plus 2x that goes in here. Okay, so just be very careful. That's all.
The X table, for I2 and CO2, why is it minus X instead of plus X?
That's because of this here, the rule.
It shifts right.
Correct.
Oh,
Yeah, the Gator rule tells us it shifts right because we plugged in the pressures that were given to us in the problem, Maria, which was 0.1. We plugged all those in here, and we got 1. 1 obviously does not equal to 81.9. So doing the Gator rule, we found out it shifted to the right. And then doing the shift to the right, it's minus x plus 2x. The reason why it's plus 2x, again, is because of the 2 here.
right.
Okay, very good. So after you plug in everything correctly, you take the square root of both sides, solve for x, and put the x back in here. All right. Yeah, okay. All right, so those are the computation problems on the exam. The last thing I want to tell you is a couple of more things here. So there's a problem on Le Chatier's principle. Go back to the Tuesday's lecture, right? Tuesday's lecture, we had a sheet involving practice problems, so it'll be similar to that on the exam. Okay. Also, you want to bring your rate law sheet to the test. Okay, you can use that for the exam. This is also plug and play. Okay, so I'll give you the equations, such as first order, it's natural log of 2 over k, half-life. So but you'll have that equation sheet. Do you know what I'm talking about? The rate law sheet? Okay. I don't think I have it here. It's in my office, so if I remember, I'll bring some over on Tuesday's exam. Okay. So bring rate law sheet to the test and plug and play to those equations. And then finally, let's just go over this really quickly here. Okay, A goes to B. So let's say you have a reaction A goes to B. Okay, so question is asking us what are the units of the rate constant K. Okay, so let's say A decays with 0 order. Right, so if A decays with 0 order, okay, we want to ask ourselves the question, what are the units of lowercase k? So we're going to put that into our rate law. Okay. So A decays with 0 order. So the rate, generally speaking, the customary units, not all the time, okay, but the customary units of rate are molarity over seconds. Okay, the SI base unit of time is seconds, and the concentration is usually in chemistry expressed as molarity. Okay, big M, moles over liter. So this will be our rate, though you may encounter some problems where it's not molarity over seconds, but this is the customary units. Okay, these are the units that are customary. Okay, so this is equal to K. Anything to the power of 0 is what? 1. Okay, 1. Okay, so what are the units of concentration? No, never mind. Okay. Okay, 1. Okay, anything to the power of 0 is 1. Okay. Okay. So the units for a 0 order is going to be molarity over second. Okay. Okay, let's say A decays with first order. Now A is 1. Okay, so what are the units of concentration? Big M, big M. So our customary units of rate are molarity over second equals K. What is M to the power of 1? Okay, it's just M. Okay, it's just M. So what will be the final units of K? Dividing it by M, this M and this M cancel. The final units of K will be 1 over second. Okay, and then the final option is that A decays with second order. If it decays with second order, then it's going to be squared. What are the units of concentration? Molar, but this is decaying with second order, so rate, the customary units of rate are molarity over seconds equals K. Okay, what is M squared? M squared is M squared. So getting our units for K here, it's going to be molarity over second M squared. Okay, one of these M's cancels out with one of these M's. So for second order decay, for this reaction A goes to B, the units of the rate constant are 1 over M times second. Okay, or you could say M to the minus 1 seconds to the minus 1. just want to get you guys to know that the rate constant has different units, okay, depending on the reaction. Okay, for this reaction, A goes to B. Okay, dependent upon how that reactant decays, you'll have different units. Obviously, if you have a different reaction, A plus B goes to C plus D. Okay, all of this will be different. All right. So that's the exam. Again, what I want you to emphasize is bring your rate law sheet so that you can plug and play those equations. And the Chate's principle, go over the part we went over on Tuesday. Did it go over on Tuesday? Anyways, I'll post that on Canvas. And then all the math is something that we saw here. Okay, by the way, if it's KC instead of KP, if it's KC, what will you put in here?
Concentration.
And what are the units of concentration?
Capital N, which is moles of solid over liters.
Yeah, so you make sure you divide it by liters. Okay, so if they give you moles, what will you do? And it's all in a 5-liter container. What will you do? Divide it by 5 liters. Okay, so make sure you divide by the volume. Don't just put moles in here. What goes in here? Moles over liter goes in here. Okay, pressure goes in here. Moles over liter goes in here. Not moles. What goes in here? Moles over liter. Moles over liter. All right, so have a good spring break. I hope it's restful and relaxing. Monday, study this. Maybe on the weekend study this, and then Tuesday take the exam. Also, your quiz is due on Tuesday, right? Yes. Unless you want that to be your drop, you can turn in quiz 2 as well. Anything else I'm missing?